So, okay, where are we? Oh, here we go. Okay, so we'll be able to do this. Okay, so just very quickly to refresh your memory, I know we did this. This was 2 weeks ago, but it doesn't matter. So, okay. So basically, we had two trusses to make. Okay, so here I'm just giving you the solution. I'm not showing you how to model it. And basically, if you want to know if you're on the right track when you're modeling something, okay, first of all, if everything's supposed to be pin connected, I just want to annotate if I have to. Okay, if everything's pin connected, then you only have what we call axial forces. In other words, the only force you have is the one that's acting longitudinally in the member. So it's either going to be a tension force, and the way the program tells you that it's a tension force is that it has a positive value, and of course it doesn't put positive here. And when it's in compression, in other words, the fibers are being pushed together. So when the member is being compressed, in other words, it's being pushed together, what the program does to tell you that it's a compression member, it puts a negative sign. And on the average, if you have a truss that is supported at the ends here like this, okay, all trusses are supported at the ends, all the members of the bottom chord will always be in tension. All the members on the top chord will always be in compression. And then the diagonals will depend on the orientation of the diagonal with respect to top and bottom chord. And those will vary from compression. Okay, and in this case, they're all in compression, okay? So they can be in tension or compression depending on the orientation and everything else. So that's something you should keep in mind. And when I'm going to ask you to, like, I'm going to give you a truss problem on the test, okay? So all I'm going to expect you to do is, like, draw the truss. And I'm even going to ask you, for example, I'm going to point here at a node. I'll probably point at this node here. I'm going to say, I'll call this node A here, okay? And I say, give me the displacements. And when I say give me the displacements, I want you to give me, for example, okay, if it's positive, you show in the x direction, you show the displacement like this, and you give me the value. If it's negative, then you show downwards and you give me the value. That's what I mean by give me the displacements, okay? And I want you to be able to interpret what those values mean, okay? So if it says, if you have a positive value of x, that means it goes from right to left. If you have a negative value, it goes from left to right. I'm sorry, the other way around. And if it's positive, it's going upwards. So that's what I mean by give me the displacement. Anyway, we'll be doing review problems. We're gonna go over this together to make sure we're on the same track. And I think most of you got this very well. So here I just asked you for the deflection at the center. Okay, so therefore this is what I got in terms of a deflection. And the reason why I'm asking for the deflections or the displacements is that you could put the wrong members in here, you'll get the right forces. It won't affect the forces, but I'll know by the displacement results if you've put in all the right members for each one. Because if you put a wrong one, you will get the wrong value here, okay? So here is the results of, and then on top of that, just to make sure that you've done it properly, to make sure, for example, this would be pinned, 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 pinned. Like a truss is always analyzed if it's pinned unless you have a continuous member, which is usually in a wooden truss, but in steel trusses, everything is pinned together. And if you double click on a member, and when you look at all the results of that member, okay, if you have any values in MX, or if you have any values in MZ, okay, if you do have value, that's because you didn't model it properly. You should only have values in the NZ column. In other words, you should only be having axial forces. That's the only place where if you'd model it properly. If you didn't release all these things properly, then you're going to start getting some MX, this is Y, I'm sorry, and you'll start seeing results here in the table. That means you haven't modeled it properly. So keep that in mind. And so this is in other words, here are the results. So I mean, this is recorded, so you'll be able to see them if you don't have enough time to check them. But the other thing I wanted to let you know is that I'm not going to do this on the final, but it stands to reason that if I put the loading, and the loading is symmetric, and I'm not going to do this on the final because I don't want, okay, but if the loading is symmetric, of course, the value in this member should be the same as the value of that member. In other words, the resultant of the forces in the member should also be symmetric. Okay, so if you look here, because the load is symmetric, all the values on this side are a mirror image of which are mirrored on this side, okay? But that's only if the loads are symmetric. If the loads are not symmetric, of course, it would vary. So that's another way of telling you if you've, understand? Of telling you if, if you have, if you've done it properly. So now, so that was the first problem. And the second one was very similar, okay? This one was, okay, so here, what happened was same thing. If you look, because it's simply supported at the ends, okay, all the top, this is also a top chord, okay, so this is part of the top chord. All the top chord here, all the values are negative, and that's the way it should be, okay. All the bottom chord, they're all positive. In other words, these are all these members are being stretched apart, all these members are being pushed together. And of course, the diagonals, it depends on, you understand, on how the forces are being resolved at the panel points, whether it's going to be in tension or in compression. Okay, so the diagonals can vary from tension and compression, and therefore in this case here, this is tension, tension, compression. And this was one of the advantages of this Howell truss, is that it kept these vertical members in compression and it kept these diagonal members in tension. And since steel likes to be, it has a better, behaves better and stronger in tension, behaves better, I should say, it has the same strength, but it behaves better or has a better resistance in tension than in compression. That was the advantage of his truss configuration, is that the longer members were all in tension and the shorter members were in compression. So that's what he had, you know, the advantage of over the other, like the Pratt or the other trusses. Okay, does anybody have any questions? Or, okay, so this is, like I said, we'll have some review trusses problems before we have the exam, and we'll be able to go over this. But if you have any questions, now's the time to ask. And so that's it for the assignment. Matter of fact, I'll close this. Okay. Okay, so now let's get into today's lecture. And today what we're going to do is basically go to the screen, share. Well, I'm going to put up the PowerPoint. I should go back up. Okay. Okay, put up the PowerPoint and put up GrayTech. Put up my ADA. I hope you have your ADA open so that we can do this simultaneously as we're, okay. I hope you have your ADA open. So today what I'm going to be doing is I'm going to show you that although ADA has an extensive amount of data built into the program when it comes to profiles, to shapes and everything else, okay? If for whatever reason you cannot find something that satisfies your design and you want to create your own cross-section for your beam, okay? And like in this case here, I made something simple. So for example, in your case, you said, well, I'd like to create my own cross-section, my beam, whereby I'm going to be having this, the flange. Okay, so this is the flange here. So here I'm going to have a flange that's 200 millimeters wide, and the thickness of the flange is going to be 20 millimeters. The web's going to be this, the web, and so on and so on. What you can do with ADA is that you can actually input this cross section and add it to the database. So then, because without assigning a cross section, ADA will not be able to run an analysis. So what you'll be able to add this into the database, and ADA will then, from the information you give it, be able to calculate the properties of the section that it needs to use to do its analysis, and so on and so on. And of course, you can do the same thing when it comes to materials. For example, ADA has 3 basic materials built into the database. You have one for steel, one for concrete, one for wood, because those are the 3 most typical materials that people design structures with. But if ever you want, you can even add aluminum, and then you have to put in all the properties of your aluminum, and then ADA will take aluminum and use that in its calculation. So you can even modify materials if you want to, but right now we'll just worry about sections. So right now what we're going to do is that we'll first worry about, okay, so what we're going to do is that in order to be able to model this properly, okay, I would like to go and create this shape into the database. So this way, when I finish creating, as I'm modeling this here, I will come back to the diagram. As I'm modeling this, I will be able to assign the properties of this cross section to this model, and therefore I will be able to continue and run my analysis. So here, okay, so here what I'm going to do is, hold on a second, I'm going to clear the screen. So what I'm going to do is, okay, so now I hope you guys have your ADA open. Like, okay, so like what I like to do when I have my ADA open, right, I always like to go to File, okay, Project Configuration. First thing I like to do is see whether I am in metric or imperial. So here, right now I'm in metric, and of course I'll put a metric shape. So that's one thing I like to check, because I don't know if you guys notice this, but with ADA, if you switch to imperial and you close your program, when you open it up again, it stays in imperial. I don't know if you noticed that, but the ADA will always keep the last values of the program that you use as the default values and come back. If the first time you open it, by default, it's metric. That's number one. Number two, these are those dialog boxes. I don't know if you guys ever tried not taking these off. You know, every time you add a member, there's that dialog box that pops up and asks you to give me the properties and whatever. So if you don't want to have that pop up in your face, you remove them. And like I said, if ever for whatever reason you find that 10 segments here is not enough because you want to get something a little bit more precise, like I tell you, 10 guys in practice is more than ample, okay, especially for trusses. You can go for 2. You only need to know the actual forces. You can go for 5. So if ever you want to have more, okay, if you ever want to have more results, you just increase here the values, okay? Number of subdivisions, so loaded members, okay? So for example, if I want to have 20 results per member, I can put here 20, 30, 40. I mean, I've seen people put 100, and I find that's ridiculous, okay? In other words, you will get a result at every 70 millimeters. Do you really need that? Okay, and the thing is that, yeah, on the screen, it doesn't make much of a difference, but if ever you need to print your results, okay, remember, if you ask for 100 results, you're just gonna get a lot of paper that will add up to very, very little benefit. Okay, so that I'm just letting you know. So this way, the loaded member, you just how many divisions you want, you know, 1, 2, 3, 4, 5, 6, and so on. And then that's it. Okay. Now, the other thing I like to do is that even before I rush and start, you know, creating my nodes, adding my members, okay, I like to be able to see on the screen what I am actually inputting. So therefore, I always like to see the length of the member. I like to see the, sometimes I want to see the material or not, but it's good to see the material. So this way you'll know if you've assigned the material, because if you don't assign the material, you will get an error message. And of course, it's nice to see what shape you've assigned to your member. And of course, I, for one, this is very nice, showing me where the X and Y axis is. You know, so I'm so used to knowing that the X axis is the one that's horizontal, the Y axis is the one that's vertical. I don't like to have that on my screen when I'm modeling, so therefore I like to remove that. This is me. If you guys want to leave it, by all means, leave it, okay? And that's it. So now I'm ready to go. So like I said, the first thing you do is, okay, you always establish, I'm going to need a node here. I'm going to need a node there. So the first thing you do when you work with ADA, establish your nodes, okay? And then of course, the smart thing to do is to literally, on paper, for each node, you should give, I mean, this one is simple, okay? You should put the coordinates of each node. So this way, when you go to ADA, you already know what to put in as you're adding your nodes. So that's number one. Okay, so basically we're going to go to structures, go to nodes, and of course I only need to have 2, 1, 2. Now of course I see that both of them are support nodes, so I'll change them right away to support nodes. Okay, now the first one is 0, 0, the second one is 7, 0, and that's what I like to do it on a piece of paper. So I'm looking for my 7 here. Okay, and therefore I've created my nodes. Now, there you go. Now, before I go anywhere, okay, and this is, I noticed, okay, before I go anywhere, because you might be panicking, you might forget, the next thing you should do is always model your supports. And like I said, by default, okay, ADA puts this type of a support. In other words, fixed. So in other words, no movement here, no movement there, and no rotation. So therefore you will get 3 reactions because it's a fixed support by default. So what I like to do is I like to go and model my supports, because as soon as if one support does not model properly, your whole analysis will be incorrect, just to let you know. Okay, and if one support is incorrect, it's unfortunate, because you'll have 95% of the problem done correctly, and because it's 5% that you do correctly, I will give you 0 for the thing, because your analysis is incorrect. Okay, so keep that in mind. That's why I don't give any partial marks, because it's not a question that you might be stressed. It's now you have to make the input proper, so that when you get the output, people can count on it 100%, and not say, "Oh, I didn't forget, I made a mistake when I modeled the support." So that's one thing you have to keep in mind. So now, what I like to do is when I do this, okay, right away I change. Now I'm going to be picking a support. Okay, so I can either pick it and then or I can just double click on it. Okay, now, as far as the support goes, the way, so if this is a roller, that means that it is free to move in this direction. In other words, it's free to move in the X direction. So therefore, this is where you free Rx. In other words, you're not going to restrict it the Rx. So that's what that means. And therefore, I'm going to be freeing in the X. Okay. I will not allow it to move up or down, and therefore I will fix it in the RY direction. And unfortunately, because it's a 3-dimensional program, okay, what you're really looking at is the Z-axis here, okay, and you're looking at the rotation about the Z-axis. But since I'm allowing it to rotate about the Z-axis, in other words, I don't want the beam to do this. I mean, that's what would happen if it was fixed. But since it's not fixed, it's free to rotate, and therefore it's able to actually have a rotational angle right at the support. And that's what we mean by rotation. And therefore, so this is because it's a 3-dimensional program. What you're aligning the rotation is about the Z-axis, and therefore we will free it about the Z-axis. So once I've done that, I press OK. And the way that I know I've done it correctly is that here you see this red dot. That means it's not free to rotate about the Z, and that's gone. And you notice that the yellow here that restricts it in the X direction is gone. So that's how graphically, if you want to be able to see, okay, versus that one. Okay, so this one means that it's fixed, fixed, fixed. So if I see that on the screen, I have to go back and modify, unless I do have a fixed support, and we will be having fixed supports today. So the nice thing about it is that when you do have a fixed support, you don't have to do anything by default. It's already been modeled that way. That's the nice thing about the program. So that's number one. So now I'm going to go back and, like make sure I'm on the activate supports, so I can, and therefore now here I have a pin. So that means it can't move in the X, it can't move in the Y, but it's still free to rotate about the Z axis, and therefore I will free it about the Z axis. And of course I have a yellow, yellow, and yellow. Perfect. Okay, so that's what I want to see. So now I model my supports, and then of course now I want to start adding my member. So I will activate the member. And of course, now I'm going to add a member. So I'm going to remember, guys, where you start is the I node, where you finish is a J node. So this way, when you're going to put information on this member, the program starts at I and goes to J. So that's all you, because if I want to put this load here, I have to know whether it's from this point to that point, or is it from that point to that point. So that's why it's important. Like, so once I click here, this becomes the I node, and that becomes a J node, okay? And I have 7 meters, that's great. Okay, so that 7 meters is great. Now, I can't do anything else at this point. I've got to go and assign the cross-sectional properties, because once I do that, then my model is complete, and then I move on to my loads, okay? Now, if you want, we can put the loads on right now, but I don't like to do that. I like to just concentrate on modeling properly, and then I can put my loads on, because once my model is modeled the way I want it, and if I need to modify my loads, whatever I need later on, I know I don't have to worry about my model anymore. So therefore, I'm going to model it properly. So right now, okay, so I cannot assign anything here, because this is the cross section I want to assign to this beam, okay? So what we're going to do is I'll show you how to do this with ADA. Okay. So, and then we'll come back to this. We'll get the, okay. So to create this cross section in ADA, I'm going to be sending you this. So these are the steps. Okay. Create a shape in ADA. Okay. Use the horizontal toolbar at the top of the screen. I'm talking about this one here. Okay. And go to common. So in other words, I want everybody to click on common. On the first row in the top ribbon, click on common. And this is what pops up. Now, once you pull down that menu, because these are pull down menus, okay, you go to shapes. And these are all the shapes that you can create in ADA, or ADA also has in its database. Now, we are going to look at I shapes, okay, because I shapes and W shapes, and so let's go to I shapes, okay. So this, what popped up in front of you is all the shapes that ADA has in the database. And these here are all the shapes that get produced in the steel mills in North America. Okay, it starts with the biggest shape here, which is a W1100. And so every shape that is milled in North America that you would find in a steel handbook, you'll find them all here. Okay. They're all here. So you have all your W shapes here. Okay. So like in other words, and it goes like all the way down, like all the way. And this is where ADA comes and takes this information when you assign a shape to your structure. It's all stored here. Now, what I'd like you to do, I'm going to just pan down very slowly. Okay. So here's all your W shapes. And then these are HPs. HPs, they look like W shape, except that in terms of, they look like they all look like H's. In other words, the size of the depth is approximately equal to the width of the flange. And if you look here, for example, the B and the D for HPs, they're very, very close, okay? And these are used as soldier piles to when you want to make retaining walls. So the HPs have the depth and the width approximately the same size. So you can see here that they are approximately the same size, and so on. Now these are welded wide flange. In other words, they look like wide flanges, except they're made from plates that are welded together, and so on. So these are all the values that you find in the steel handbook, and so on and so on. So this is where all that information is stored. Now I just want you to go pan down all the way to the end of the spreadsheet. Like I'm just dragging down now. I'm dragging down, okay? Now, I've already created one. Okay, so I'm going to delete this and I'm going to start over. Okay, I've already created one, so I'm going to delete it and I'm going to start over. Sorry, I apologize. Because I had, this is probably from last year, and anyways. Okay, so what you need to do now is you want to add another row to the spreadsheet. So you press on the plus sign. Okay, and you'll see all the instructions are here. So if you go back to the PowerPoint, or if you go to the video when I send you the video, okay. Now, what you need to do is you need to give it a name. Okay, so you have to designate a name here. Okay, so what do you want to call it? Like, you can call it anything, but you have to remember what you call it. That's where ADA is going to store it. Okay. It's going to store it under that name. So for example, in my case here, what I like to do is I like to call this, like, for example, a W400 by, let's say, 200. In other words, the width of the flange. Okay. I just doesn't matter what you call it. And then you can also give it an imperial designation here. Okay. If you want, doesn't matter. You can call it exactly the same thing, or you can convert those to imperial values. In other words, that would be a W16 by 8. Okay. And then after that, you know that the material here is steel, because if you happen to be making wood, you would change that to wood. Okay, but we'll leave it as steel. And then here, okay, so here is the type. Now, if you click on it, okay, these are the different types. So for example, if you happen to have a HP, if you happen to have an M, an S, a W, a welded wide flange, a super light beam, you would actually change that. And that's once you pick the type here. So I'm going to call this, like, it almost looks like a wide flange. I'll leave it at wide flange. And what ADA is going to do is going to take this section that you created, and when you go to the properties, you're going to be looking under wide flange, and that's where that information is going to be stored for you, okay? That's what you have to keep in mind. So if I put here W, when I go to the properties, I will find it under the W shapes. If I would have changed it to WWF, when I go to a property, I would have found it under the WWF shapes, and so on and so on, okay? Now, if, okay, I want you to right click, and I want you to right click on the W there and put details, okay? So if you're not sure what these cells are here, okay, because this is where you have to input the information. If you're not sure where these cells are here, this is the diagram that the program offers you to let you know what D is, what B is. Like, I know these like the back of my hand. I mean, I've been practicing for 40 years plus, you understand? So for me, it's okay. But for you guys that aren't really sure, if you're not really sure what is the value of D, well, here it tells you D is the actual depth of, in other words, from outside to outside of both your flanges, okay? So that would be your D value. So right here, okay, and then what is the B? B is the width of the flange. So I would put the value of the width there. What is W? W is always the thickness of the web, and T is always the thickness of the flanges, okay? So now, if you don't happen to have the value of K1, in other words, if this doesn't happen to have a little fillet in here, don't worry about it. You'll leave it as 0. And it will take that into consideration when it calculates everything else. And so you don't necessarily have to put in all the values here, but if you do have the more specific geometry of your cross section here, because usually if this was a rolled section, you would have a value of K, you would have a value of K1. These are all, you find these in the steel books, okay? So right now, we know what we're looking at. So therefore, the D is the depth, B is the width, T is the thickness of the flange, W is the thickness of the web. So I'm going to press OK. So now I'm going to come here and start. So in other words, okay, I'm going to go back to the other, I'm going to show you so we can look at the diagram together. So here we go, okay? So here, so in other words, what is D? D is 400, okay? 400. Now, what is the nominal depth? Now, usually what they do in steel is that they have what they call nominal depth. In other words, it's approximately 400, and then in steel they have what they call 410, okay? But in our case, we will use the nominal depth is exactly the same as our depth. So I will put 400, but okay, 400. Now, what is B? B is 200. And what is W? Well, W is the thickness of the web, we said, so that's 10. And what is T? T is 20. So now I don't have a K value because it's perpendicular. It's perpendicular, okay? And I don't have a K1 value, okay? And so on. Now, what's nice about ADA is that if you pan over, okay, as soon as you put in information of B, D, W, T, look what ADA does. It tells you what the cross-sectional area of your section, tells you what your moment of inertia is with respect to the x-axis. It tells you what your section modulus is with respect to the SX, RX, okay, ZX, the plastic section modulus. We didn't get into this, but this is where you can have the whole section plastified before it fails. And then you have everything with respect to the y-axis. So this gets automatically calculated by the program, and this is the values that ADA uses to do its analysis. It needs to know the IX. If you want to know stresses, it needs to know the SX. If you want, or the ZX, and if you want to know the RX when it needs to do calculations regarding compression members and so on. So this is where it would come back and get all the data it needs to do whatever you want in terms of results. Now, in your case, you're only doing forces, and therefore it would only worry about the IX value and so on. But if ever you would ask to also give you the stresses. So that's it. So now that everything is here and we've created this section, I can press OK. Before I press OK, is everybody good? Have you all put in the right values in the right cells? Are we good to go?
Yeah.
Okay, thank you, Emmanuel. Okay, so now that I've created my profile, right? Now that I've created my shape, I should say, now I can, of course, I'm on members here. I can double click on it. I can click on it and then go to properties. Now remember, we said that it was a steel, okay? And we said that it was a W shape. That's what we told the program that we were going to put the property. So therefore I go to W shape. Now, if you go and look at, you've created a W400 as your nominal depth. So it would be in here. Now, if you would have given it a name, like for example, you would have called it My Beam, it would have been at the very bottom here. You would have seen it like, so sometimes you might want to give it a strange name so that the program puts it at the very end. But in this case here, I put it at a 400. And of course, it would only be one section because I've only created one section on this one. Okay. And if you go click here, you'll see that it's got the same, everything that you've inputted, like in other words, 200, 100, and so on and so on. And it gives you all the sectional properties and everything else. Okay. So now you know that this is the one you've just created. And of course, we press OK. Now, as far as the materials go, I'm telling you that it was made with Canadian steel in this case. So I'm going to go to materials. And I'm going to go to steel. I'm going to go to the G40, G40, G20. This should have been a 20, not a 40. That's a typo, guys. I apologize. G40 20.350W. So please pick this one. This is a typo. This is G40.21. There's no G20 in Canadian steel. That's just a typo. And of course, here I say calculate it with the self-weight of the member. So therefore, I'm going to add the dead load just to make sure. And I'm basically done. So I press OK. So here I have a W400 by 200, the one that I've created. That's what I called it. I'm using this steel. That's what I want to use. And of course, the member is 7 meters long. So, and that was the last thing I had to worry about in my model. In other words, making sure I assign the right material, I assign the right shape, and I've got the right length. And therefore, now I can go back to my visual options. I don't need to see that anymore. And therefore, I can just remove it from the screen so that when I look at my results, it will not be there, and so on. So now my model is complete. I call that phase one. Phase two, I go to my loads now. So to go to my loads, of course, I have to tell the program, classify my loads into different load cases. Now this here is going to be simple because we're only going to have one load, okay? But normally you would have dead loads, you would have snow loads, you would have live loads, you would have wind loads, and so on and so on. And that's why you create load cases. But in our case, we'll put everything under one load case and not, so we will define a load case. So here, this is the dead load. Like I said, the program by default keeps dead to calculate the self-weight of the member, and therefore you need to create another load case. And now here you can call it whatever you want. I can call it live load or whatever, okay? You don't have to define your load. If you define your load, the program can actually generate load combinations for you according to the National Building Code. And that's where you would go define it. So if you don't want to waste your time defining the load, don't bother, okay? But if you do want the program, then you would come here. And if it would be a live load, then you would put it under live load. And therefore, when you have your dead load, live load, superimposed dead load, so on, the code knows how to generate the different load combination according to National Building Code, and it will do that for you automatically. That's what the program can do. I press OK. Now, when I'm ready to apply loads, I got to remember I have to activate the load, because first, this is activate the model, right? The structure mode, and this is the load case. I have to activate that, and I'm telling it to put everything under live load. Save the project, yes. Where are we going to save it? Save it under desktop. Let's go to Dawson. Save it. Okay, there you go. So now I'm ready to, now I'm ready to add the load. So therefore, make sure you got the member activated here. Okay, pick the member, right click, go to properties. Now, I have a load of 50 kilonewtons per meter. So therefore, I'm going to put here minus 50. And of course, it's going to jump here to be minus 50. So that takes care of that. And of course, I have a concentrated load. So therefore, I'm going to change the tab. Okay. Now, this is where it's important because like I said, if you clicked here to create the member and then you went there and you click there, well, that's I and that's J, okay? And therefore, the computer will start, whatever information you give here, it will start from this node here. If you happen to click there and add it there, then you're gonna have to go backwards or the other way. So that's why it's important how you remember how you added the member. And so therefore, so here I started here, therefore I know that it's at 2 meters away, and the force is minus 100. Oops, I put an equal sign by mistake. I should have put a minus sign. Minus 100. And of course, as far as this is good, 90 degrees global, it's perpendicular global, 90 degrees, everything's good. Press OK. Now, there you go. Now, of course, if you want to see this a little bit neater, you just do that, and then you can play with it as you want, okay? So there are my loads. There's my concentrated load here of 100 kilonewtons per meter, okay? And so on, and 50 kilonewtons, 100 kilonewton concentrated load, and so on. Now I'm ready to, I've got no more loads, so therefore I only have to go and tell the computer how to combine my loads. And of course, here it's simple. I only have one load. As a matter of fact, I have two load cases. I have the self-weight and the superimposed live load. So I will go to load combination. Now don't put define, because this is where, I mean, don't put generate, because the program will generate all the ones that you've added. I'm going to put define, and then here, okay, call it live. And then you can call it whatever you want. Plus self, like sometimes it's good to put things that you'll remember what you're looking at. Plus self weight, you understand? And now this is where, for example, so here you're going to have one, you're going to have two. You're going to have the live load, and here you're going to have the self weight, which the computer considers as a dead load. So therefore, now I've added both. And in theory, when you're doing design, these load factors will change, and you'll learn that next year in limit states design, okay? I don't waste my time this year because you'll probably forget about it next year anyway. So, okay, so now I've done my load combination. So step one, modeling. Step two, my load case. Step three, tell the computer how to combine my loads. And then when I'm ready, of course, I run the analysis, okay? And analyze. Now, what's nice about it, calculation is complete. You can consult your results, okay? Now, in this case here, you want to see the reactions and you want to see the deflection, okay? So first of all, you activate which load you want to see. So therefore, if I go to view results, okay, I want to see the reactions. Now, I'm going to put Rx, but it should be 0. And when you look at deflections, you're always looking at deflection with respect to those strong axes. So that's what you're looking at. So the deflection with respect to the strong axis, the reactions. You can put Rx, Ry, and all that. And you press OK, apply, OK. So there's your reactions. And there's your deflection. And of course, it's very important that, so what I'm going to expect you to do, if I give you a problem like this, what I expect you to do is, you're going to take your paper. Don't make a screenshot. I will give you 0 for a screenshot. I want you to put this on a piece of paper, okay? So if you put this on, you give me a screenshot, I will give you, even if you get it right, I will give you 0, because I want you to be able to put this on a piece of paper and be able to interpret the results. So do it on a piece of paper. So what I'm going to expect you to do, of course, is you draw, and of course here you either put on your sheet that all supports are in kilonewtons and all deflections are in millimeter, or actually put the 34 millimeters. Okay. Now the reason why it says minus 34 here is because it's going from its original position downwards. If for whatever reason it would have deflected upwards, it would have given you a positive value. So that's why it puts a minus 34 here. It tells you in which direction that the displacement is actually occurring. And that would be it. Did you guys get the same results?
Yeah, the same thing as you.
Fantastic. So it means you've done everything correctly, okay? Or we both did, or we both did it wrong. How's that? Did anybody not get these results? Now's the time to let me know. Don't be shy, guys. Now's the time, because then we'll see where the glitch might be. So I guess we can go on. I guess I'm not getting any answers. I guess you all got the same results. And the ones that didn't get the results, if you're too embarrassed to say so, it's your loss, not mine. Trust me. Okay. So now I'm going to go on. Now we're going to talk about, so here's a step-by-step description of what we just did. So I'm going to be sending you this file. Okay. And you can review it here if anything. And then of course, R, Y, and deflection about it, and so on and so on. So now, we'll talk about frames, okay? We'll talk about frames. So I'm going to talk about frames. And now you have, this is called rigid frames. In other words, all the joints here, they're all fixed. Everything, it's almost as if like for example, when you look at a concrete structure, that frame is a rigid frame. In other words, all the members are sort of like cemented together. And if you're looking at a steel structure, if you want to create a rigid frame with a steel structure, then everything has to be welded together and stiffened and so on and so on. So you have what we call rigid frames. Okay. Now, why do we have frames? Because when you have lateral loads, the frame itself will be able to resist the lateral load. You won't need to have any bracing system to be able to transmit the lateral loads down to the foundation. So frames allow you to transmit. So frames are one way of taking care of lateral loads, okay? And therefore you can rely on the frame to be the element that's going to be the lateral load resistant system for you. Now, in this case here, the reason why you have a pin-ended, fixed-ended, because sometimes you will pin the frame to your foundations, and sometimes you will fix your frame to your foundation. So depending if you can fix it, you will fix them. If you can't fix it, then they will be pinned. Now, the only difference here is that when I have this, I'm going to have, depending on the direction of the lateral load, I'm going to have one reaction here and one reaction there because it's pinned. That means this thing is free to rotate. So therefore, there's going to be no restrictions here in terms of moment. So for example, if I put a load here, I'm going to have a reaction this way and I'm going to have a reaction that way. Okay. Now, when it's fixed at the foundation level, then not only do I have this reaction and this reaction, but I also have a moment that's going to stop this thing from curving. Okay, it's going to stay straight and then it's going to, so therefore that's what this is. So when it's fixed, I have 3 unknowns. When it's pinned, I have 2 unknowns. In other words, just like for a beam, when it's pinned, this thing is free to rotate, and I have that angle there of rotation. When it's fixed, well, that thing stays at, this angle here stays at 90 degrees with respect to the support. That's what we mean by fixed. When these things are all fixed, these things will rotate. You understand? They will rotate. In other words, they will deform. But when we say that it's fixed, this 90-degree angle here will always stay at 90 degrees. And if it doesn't stay at 90 degrees, then it's not considered fixed. So all these angles will actually stay at, or should stay at 90 degrees if you're going to consider this to be completely fixed. Fixed. So that's what happens here. Okay, so this is for rigid structures. Now, this is very, very common to use rigid structures when you're doing concrete because it's very easy to create a rigid structure. And then how you're going to fix it to your foundation, well, it will depend on a number of factors, but you can either make it pinned or you can make it fixed. That's going to be up to you. So this is good for concrete. Okay, very good for concrete. When you're doing a concrete structure, you're going to have a rigid frame. That's number one. Then the other type of frames you have, of course, are these here. These are called brace frames, okay? Brace frames is what you do in structural steel. So if you ever go to New York City, all the buildings, all the high-rise are all made out of structural steel. And if ever you look at the skeleton or the frame, I should say the framework of those buildings, okay, you'll see some kind of bracing system that will allow the lateral loads. For example, the load that blows up here, this will allow that load to make its way all the way down to the foundations. So that's what these things do. Like for example, this lateral, if you notice that this is a K-truss, okay, so this is a K-truss. So in other words, what these things are, they're like trusses that are put in a vertical direction. And what they do is that when I put a load here and I put a load here, as the wind or the earthquake creates lateral loads, well, this system will allow the load to make its way down to the foundations where hopefully it has a resistance to be able to keep everything stable. Now, of course, this thing will displace a bit, but at least it will not collapse, okay? So if I wouldn't have a frame in here, when I would have a lateral load, and if this wasn't a rigid frame, well, as soon as the load would go on it, the whole thing would just collapse on you. So these are brace frames, and this is very, very typical for structural steel, okay, because it's easier to put in a brace than to actually do a frame with structural steel. It's less expensive. And for concrete, you do a rigid frame because it's much easier to make a rigid frame than to make a brace frame in concrete. And if you want, I've seen this, okay, I've seen this, where you can have a hybrid of the two. Like, in other words, you can have a concrete structure, and in between you can put these braces, okay, and have them actually, they're called seismic braces. In other words, what they do, they tend to dissipate the energy of the earthquake, and therefore it helps to reduce the stiffness of your frame. So there's, you can also have a hybrid system, and like I said, and that bracing system for earthquakes, that was developed by a professor at Concordia, about 20 years ago, and it's been used here in Montreal. And I don't know how popular it is now, but that's another way you can do it. So like I said, so the type of frame will depend on the type of material that you're using, and if it's steel, you'll be using a brace frame. If it's concrete, you'll be using a rigid frame. Okay, so that's just to give you a general overview of frames. Now, this is a frame also. In other words, a frame is able to stand on its own, okay, and be able to resist lateral loads, okay? Or in this case, even if we had a gravity load in here, it should be able to resist a gravity load. Because, for example, if this was pinned here, like this, instead of fixed, if this was pinned and I had a gravity load in here, right? Well, what would happen is that this thing would just rotate this way and collapse. Okay, that means there would be no resistance here. In other words, it would act like a door hinge. I would put a load there, and therefore the door would just go and bang, hit the ground. So what this does is that whatever rotation the gravity load would cause, well, this will counteract that rotation and keep the structure up. In this case, and now here for the lateral loads, since the lateral loads wants to make this thing turn over this way, what this will do will create a resisting rotation that way to keep everything standing up. So that's what we mean by fixed. Like, now this thing is no longer free to rotate. It is going to actually stay there and resist whatever rotation this member wants to undergo. And because it resists that rotation, we will have a reaction of a moment at the support area. So here we would have three unknowns. We have one in the y, one in the x, and then one in the mz, okay? Now, let's start a new file, and we'll go ahead and do this. Okay, now here, what I want you to realize is calculate the reactions and the displacement at node A, okay? And then use a W16 by 31 for all members. I use G, again, I put G, this should be G40, okay? Now, the strong axes of the vertical members are perpendicular to the load. So what this means is, okay, since this is a Y flange section. So a Y flange section, what happens is, this is the strong axis. In other words, where the flanges are parallel, this is the XX axis, okay? So when the program by default places them in a certain direction. So for example, if the program happened, if I take a cross section here, like this, and if the program happened to put it in this direction, well, it's not, the wind is not acting with respect to the strong axis, it's respecting with the weak axis. In other words, it's the YY axis, and the same thing here. So therefore, you're going to have to make sure that the orientation of the axes of these members are in the same thing with this one. This one normally, like this would be how you would place it, so that when you put a gravity load, it would be bending about the strong axis. So you also have to make sure that this is in the right orientation. By default, the program puts this one usually in this direction, but I'll show you how you can check that. So after you finish modeling, you're going to have to go back and see if the program actually put the axes that you want to resist your loads in the right direction. And that's what I'm going to show you to do here. Okay, so what I'm going to do now is I'm going to start a new file. Okay. Now, again, whenever I start a file, I always go to File, I go to Project Configuration, and I go to Preferences. First of all, I'm doing everything in Imperial, so I'm going to put Imperial for my shapes and Imperial for my geometry. Okay, so that's one thing. So here I've changed that right away. And at the same time, I'm going to remove these dialog boxes because I don't want them to pop up as I'm doing my model. And of course, like I said, for me, 1 and 10 is ample. I don't need more than that. And if ever I do, I can simply come back here, change this to whatever I want, rerun my analysis, and I'll get more results if I need to have something. But for 1 and 10 is more than ample. And like I said, before I start anything, I like to see the length of my members. Sometimes I like to see the material, the shape, and I don't like to see that axis in my face. I apply that. Now, before you rush to ADA, right, what you should do is like anything, okay, I'm going to need a node here. I'm going to need a node here. I'm going to need a node here, and I'm going to need a node there. Because this node will allow me to add this member, add that member, add that member. So the first thing you have to visualize, where am I going to be placing my nodes? That's number one. And number two, okay, what you should do is look at, for example, if this is going to be your y-axis and this is going to be your x-axis here, okay, what I like to do is on my sheet of paper here, for example, I'm moving 0 in the x, I'm moving how far up in the y-axis. So 6 minus 15, 9 feet. So that would be the coordinate of that node. Here, the coordinate of this node would be 0 because I'm moving nowhere along the x, and 15. So I like to do this on a sheet of paper before I rush to ADA. So this way I can just look at my paper and put the values as I open up the spreadsheet. And then if this is the next node, I know that this I'm moving along the x, I'm moving by 10 feet. And I'm moving along 15 feet in the y direction. And then here I'm moving 10 feet in the x direction, and I know I'm moving 0 direction in the y. So I like to put my coordinates right away. So therefore, I don't have to do any mental calculation. I can even use my calculator to help me establish these coordinates. And remember, this is the x and the y. And by doing that, when I go to my structures, and I go here, I go to structures, and I go to nodes. Well, first of all, I know I need to do 1, 2, 3, 4. So I can right away 1, 2, 3, 4. So I can already open up 4 rows to put in my nodes. The first one is a normal node, and the x is 0, and the y is 9. So therefore, I know what to put here. And then the second one, the x is 0, the y is 15. Now the third one, the x is 10, and the y is 15. And the last one, the x is 10, and the, I'm sorry, wrong, I'm in the wrong, sorry, I apologize, that the x is 10, and of course the y is 0. So that's what helps. So this way, instead of playing guessing games and trying to do this in my head, and like I like to do that on my sheet of paper. And if I'm happy with my coordinates, and of course I know that this is a support node, so right away I'll change that to a support node. Okay, press OK. So there you go. Now, what's nice about this is I know by default that the support is fixed. So therefore, I don't have to go and model my support. My support was by default modeled by the program. So therefore, I don't. So if it wasn't, then I would have to go in there and modify it. And of course, everything should be fixed, because you're not allowing the rotation. So once you've done that, so my supports are good. Now the next thing I'm going to do is I'm going to activate my members. And of course, again, okay, I'm going to add members. So I'm going to go from I to J, from I to J. I do this purposely, so I to J. So I know which is my I, which is my J, okay? Or sometimes what I like to do is I like to go from I to J and so on and so on. So now, when I look at my lengths, 6 feet, 10 feet, 15 feet, great. Okay, so that means that that's great. my nodes are the right place. That's exactly the length of my member. So if I want to get that out of my face, I can simply go back, and now I've confirmed that the lengths are good. I could remove that, less things to look at. Now, what's next is, of course, I have to assign the shape as well as the materials. So I will choose all the materials at once by drawing a window, okay? They will all have the same shape and the same materials, and then I will right click, go to properties, and of course, because I went to I've already told them I'm working in Imperial. When I go to my steel shapes, I should have the Imperial shapes in the database here. So when I go to the W shapes, I'm looking for a W16. So in other words, it's got a nominal depth of 16 inches, which is here. And it has 31 pounds per foot. Here's my W16 by 31, okay? So there you go. And there's going to be the shape. And then as far as the material goes, I am going to be using G40. I'm sorry, just like I said, that was a typo. I should have corrected that. G40, G40.21. And like this used to be old samples, but G40.21, 350W. So in other words, this is, I don't want to get too technical, but this means it has a yield strength of 350 megapascals, and that's weldable steel. And of course, if you want, you can put this in right now, okay? And as far as I'm concerned, everything is okay. So I press okay. Now, the last thing I need to worry about, okay, the last thing I need, so everything looks okay here. So I'm gonna go and remove that information from the screen so that it doesn't clutter up my screen. Now, the last thing that you want to look at is, are the beams, or I should say, are the sections, either, you know, columns and stuff, are the sections in the right orientation? In other words, do I have the, you know, like the load is being, I said that the strong axis in the member is perpendicular to the load. In other words, here, if I'm going to look at this, in other words, is the flange on this side, that's the strong axis. Is the flange on this side, that's the strong axis. In other words, is that how the program actually put in the thing? So, and then of course, is that how the shape has been placed by the program? And I have to go and check that. So what I'm going to do is, excuse me. So what I'm going to do is I'm going to go to mouse. Okay. So first thing I want to do is I'm going to go back to the visual options here. Okay. I'm going to let everybody pick the visual options. And I'm going to go to attributes. Is everybody there? Tell me if I'm going too fast, guys. Go to visual options, go to attributes, and click here, 3D display. Find right underneath material, you'll find 3D display. Click that, okay? And what the program does, it will display your member in a 3D shape. So if you press apply, there's your member, okay? Now, you can't really tell, but this one looks good. In other words, it looks like the flange is there, the flange is there, and this one looks like it's in the wrong orientation. But if you want to make sure that you're looking at it properly, what you can do is go to the top ribbon, go to the bottom row here, and you'll see camera. Okay. Oh, I should have maybe, okay. I have all of this on the next page, so you'll be able to review this, okay? So you go to camera, okay, I should have, you know, so this way you guys can follow what's also on the screen here. So you go to camera, there's that little triangle where you can pull down the menu. And here I'm telling you that go to camera and go to ISO front. ISO front right, okay? And that gives you an idea of what it looks like. Okay, so you can see that the wind or the loads are being applied in this direction, but the flanges are not perpendicular to how you're applying the load. So therefore, you're going to have to rotate these members. This one's in the right because the top and the bottom flange are in the right direction. So we need to rotate these. So what we're going to do is we're going to rotate them. Now, how do you rotate them? First of all, make sure your on members are activated, okay? Pick one of them, just pick one, okay? Pick one member, make sure it's highlighted. At the vertical menu bar, you see I'm pointing at rotate. It's about the fourth, like if you, well, excluding the one that's been grayed out. 1, 2, 3. The fourth one from the bottom, there's like a little circle with an arrow. That means rotate. You click on that. Okay. Now, before you go there, I skipped a step. Okay. Cancel, annually, cancel. Now, before you go there, you need to know what node. I know this because I got the nodes in my head, but you need to know what node you're rotating about. So what you do is you go back to options here. I have it here. Okay, so okay, so here you go to elements and you go to numbers. So make sure that the nodes, the numbers of the nodes, you can see them on the screen, because the program needs to know rotate with respect to which node. Therefore, you can tell it which node by having. So this is node number 1, number 2, number 3, number 4. So there, I'm sorry, I skipped a step. So, okay, specify and press enter. Now, so what you're going to do is you're going to go, I've got that highlighted. I'm going to rotate. Now, I'm going to go from 90 degrees. I'm going to go to 0 degrees. In other words, turn it back to, okay, and what's the node? And of course, the node is node number 1, according to what I see on the screen. And I press OK. And there you go. So now the program has oriented the section in the right direction that you're going to be applying the load. Now, if you didn't orient it, trust me, your displacement is going to be far greater if you hadn't done that properly. Now, I'd like you guys to do the same thing for this member here. So go ahead and do it. In other words, highlight the member, go to rotate. Again, you're going from a 90 degree to a 0 degree. You're rotating it by 90 degrees. And the node you're rotating about is node number 4. Press OK. And there you go. So there you go. And now you've got the sections in the right orientation in order to do your analysis. If you weren't going to rotate them, your analysis was going to be incorrect because you are pushing the force against the weak axis, and of course the weak axis is not as strong as a strong axis, and your displacements would probably be 2 to 3 times more than what they were actually going to be. So is that okay with everybody, or do you want me to repeat anything? Now, you can keep everything like this, but if you want to go back to the view that you normally look at when you're doing ADA, because I don't like to work in 3D, I like to work into simple lines. So basically, I'm going to go back here. I'm going to go back to attributes. I'm going to take off the 3D display, apply, so I can just get sticks again. And at the same time, I like to see what I'm usually seeing. So I go back to the camera and I go to, I'm sorry, I have it here. Go back to camera. And okay, and there you go. So now it's back to the way it was that you used to seeing. So it's up to you guys. You can leave it in 3D, but I find that when I'm going to look at my results, it's going to be much easier for me to look at it from this view.
What did you click to get this view?
Oh, you got to go back to camera.
Yeah.
Okay, and go to right.
Okay, perfect. Thank you.
I apologize. I skipped a step. Okay. Okay. So now, okay. So there, I apologize. So this is the right view. As a matter of fact, by default, when you look at your thing, it gives you by default the right view when you open up ADA. So I apologize for not saying that at the beginning. Okay. And like I said, if ever you want to look at from front, right, and guys, go when you have a chance, play with this, play with it, like for example, ISO left, you understand, of course, and that's how you're going to see it from there, like have fun with it. There's nothing to stop you from, if you want to see it from above, like a plan view, if you want to see it from the rear, if you want to see it. So that way, and this, what's nice about this is that when you're doing a 3D, it gives you the chance of rotating the building easily. And of course, we want to do it the right, okay? So, just go ahead. And like I said, if you guys like to see it in 3D because it gives you a better idea of what the members look like, leave it in 3D. It's up to you. I for one, that's, there's nothing wrong with leaving it in 3D. So in other words, if you want to go back and leave it in 3D, you simply go to attributes, click on 3D display, press OK, and there you have it in 3D. And what's nice about it, here you can see where the flanges are. You can see where the web is, so you know that everything's in the right direction. It's up to you. I'm not telling you, like whatever you feel more comfortable with working with the program. I like to work with lines, and therefore, oh, sorry, I will simply remove this. So this is nothing that you have to do. It's up to you. I'm just letting you know. Now, what you need to do now, of course, my model is complete. In other words, I've got the model in, I've got the right orientation for the axes of my members. Now I'm ready to move on to my loads. So I'm going to go back here so we can look at the loads. So basically, I'm only going to be applying a lateral load to this member here, okay? And I'm going to look at what happens. So of course, I'm going to go to loads, load cases. I'm going to define a load case. And now here, I'm going to leave that dead load there, but I'm going to call this lateral. A lateral load. I'm not even going to define it, but if this was a wind load, I would define it as a wind load, but define this as a lateral load. Okay. So now that I'm ready to apply the load, of course, I'm going to activate the load case first of all, and I'm going to go to a lateral, save the project. Yes. It always doesn't even go back to where I saved it the first time. And now I am ready to apply a load to this here, right? So basically I'm working in kips. Now I know a kip is 1,000. I don't even want to do that mental math. So therefore I'm going to change the units and I'm going to change it to kips per foot. And then if you don't want to go to 2 decimal places, leave it at 1 decimal place. It's up to you. And of course, now it's going downwards towards the member. So I'm going to be putting -1, -1, and it's going to give me a -1 there. But what's important here is the orientation. How is the load applied? Now, if you remember that this here is how the member is actually, okay? So the load is being applied with respect to the strong axis, and therefore, what you're going to do here, you say apply it to the strong axis, okay? And by doing that, you should have it in the right orientation. And there you go, okay? So that's how you make sure you tell the program to apply it to the strong axis, and it's going to be, and you put a -1 because it's going to be going like as if it was horizontal, and it's going to be going, you know, down across the strong axis. And that's how you apply the load. Now, if you weren't going to change the orientation, I really don't know how you would have been able to do that, but that's how you do it with ADA. So in other words, you can have, I remember when we talked about trusses, I showed you what horizontal global is, what global is, and so on, strong axes, and I showed you that on the truss, and that's where you apply it here also. So the orientation is going to be, now it's all good. So I'm ready to go ahead. Now I've only got 1 load case, so therefore it's very simple. I go back to loads, I go to load combination. I'm going to define my load combination. Now I'm going to call this one lateral. I can call it whatever I want, but usually I like to give names that I know what I'm analyzing. Call it a lateral load. And of course, I don't want to see the dead load right now. I just want to see the lateral load. So I'm going to put my lateral load here, press OK. So model is complete, load case are complete, load combination are complete. Now I'm ready to run my analysis. So I press analysis, save the project, yes, and analyze. And I can consult my results. Now, if you get an error message here, it's because you skipped a step somewhere. You either didn't assign the section, you didn't assign the material, you probably created some kind of instability. Anyway, if something's wrong, this is where you're going to get your error message, and hopefully you can resolve it. In this case, we've got our results. And even if you don't get an error message, if you haven't modeled it properly, it can still be wrong. So at least, you know, you were able. So here we're talking about lateral loads. Okay. Now, guys, I know you guys like to see everything on the screen. Unfortunately, okay, what I don't like about ADA, they don't show you the moments on the screen, even if you ask for the results. Here, I'll show you, okay? So what we're going to do is, for example, we're going to ask for the results. We're going to ask for Rx, Ry, because we should have R, okay, and we're going to ask for the deflection about the strong axis. Okay, and we're going to ask for MZ because that's the rotation. But you'll see that you won't see MZ on the screen. Okay, so what I recommend you do, okay, so what I recommend you do is this, okay? is that instead of trying to see it on the screen, because here you have, okay, it tells you what it is. Okay, what you do is you activate support. Activate support here, okay? And you double click on the support and it gives you the reaction. So here, this is what I'm gonna, this is the best way to do it, so this way you don't make a mistake. Okay, so right away, I see I have an Rx of -6 kips. So on the exam, I want you to do this. You do a sketch and you put it in the right direction and you put 6 kips. Okay. Now, if on the exam you give me -6 kips and you don't show me the direction, you'll get 0 for the problem. If on the exam you give me the direction, you put -6 kips, you will get 0 for the problem. Okay. This is to tell you what direction you're looking at. So you should be able to interpret this and put it on your diagram. So when I look at it, I know that the reaction is in this direction. Ry is 0, so you don't put anything. So that's why. Now MZ, the program tells you that when it's positive, it takes that to be a counterclockwise moment. Therefore, MZ, you showed to me in a counterclockwise direction, and then you give me the value of 72. Now, you either put 72 kips foot here, or you put, values are in kips and kip foot, as long as I know that you gave me the units. Okay, now so that's where you should go look for your reaction. So this will tell you the value of MZ. Negative means it's clockwise, positive counterclockwise. So if it's positive, I want you to show it to me as a counterclockwise moment. And then if I have a negative value here, it goes from right to left. If I would have, we'll see some positive and negative values for Ry. So if it's positive, it's going up. If it's negative, it's going down. I want you to give me the right direction. I want you to be able to understand and interpret what these signs mean that the program cannot draw for you. Okay. As a matter of fact, if you look here, it even gives you the direction. And look what's nice about the program. Okay. I'm going to press OK. That's what I like about this program. Okay. Look at this. Did it put a negative sign for 6? No. What did it do? It showed you what direction the 6 was in. You see that? And that's how I expect you to do it. So the program would be incorrect if it showed me the direction and then put a -6. That means that if I would see this direction, I would see a negative number. That means I'd have to change it and put in the other direction. And unfortunately, the MZ is there, but I can't see it. Okay, so that's why I like to go and make sure I activate support, double click on the support, and I get all my reactions. And that's how I don't forget one. Because year after year, people they go to get on the screen, they always forget the MZ. They forget the MZ, and I give them 0 for the problem. Okay, so don't do yourself a favor, learn on how to go get the results in table form. Okay, that's number 1. Let me clear this drawing. Okay, so now that's that. Now, if I want to know the displacement, I tell you, what is the displacement of A? Well, activate the joint here, activate the node, and therefore, if I double click on the node, it gives me the displacement. Okay, so here it says 0.77. So on your exam, what I expect you to do, okay, I expect you to put an arrow here like this because it's positive, it's going from left to right, and I like you to put 0.77 inches. Now, if there's also displacement in the y direction, if it's negative, you're going to show downwards. If it's positive, it's going to show upward. In this case here, it hasn't. This displacement in the y direction is insignificant, therefore it didn't give you anything. Okay, so the best thing to do to get the displacements, okay, because here it tells you how much this thing has displaced. But if I tell you I want to know the displacement of this node, you simply activate the node. You activate the node, and then you double click on the node, and you'll get all the information here. And just remember, interpret the signs. Positive in the X, negative in the X. Positive in the Y, negative in the Y. Okay, so interpret how you're supposed to draw it on your diagram. And this is a perfect example of, it shows you the right direction and it gives you the value. So you're supposed to show me the direction and the value. That's what's important. So the negative and positive is just for you to how to interpret the results of the program. Not that I put a direction, I put a negative value, that is wrong. Okay, and I will mark it wrong. Okay, so here we go. Let me just clear the screen. So, and okay, and basically that's it. Now, of course, if I wanted to see some bending moments and all that, then of course I would go to my results. I should have some bending moments in this thing. So I would look at MX, and I can get some bending moments. I want to see some shears, apply. So there's the bending moment that's happening in my frame, and so on and so on. So then, of course, when I would be designing this, I would, make sure the members were strong enough to resist these forces. Okay, so that's the second. Now we're going to actually learn how to do, so this is a simple frame. Okay, in other words, this is typical. For example, you see this on highways, you understand, where, for example, they have something come out cantilever and they have a beam and they have some kind of sign hanging out here. Okay, so this is a very typical, and you see it's all standing by itself. Well, that's how it's analyzed, and then that's how it's designed. In other words, the analysis tells you the forces that these members are going to be subjected to, how much of it is going to be displacing, is it tolerable, in other words, and that's what you're going to be doing. So this in itself is a rigid frame. Okay, a rigid frame means that it's able to stand on its own and be able to resist lateral loads. Okay, so that takes care of this one. We will move on to the next one. Okay, now, so all the instructions are here. I'm going to send you this anyway. So now we're going to learn how to we're going to learn how to, so let's start a new file. Let's start a new file here. Okay. Okay. Now, here, what we're going to learn how to do is, for example, I have a rigid frame. Okay, it's made out of concrete. It's a 3-story building. Okay, and these are the bays of each. So in other words, the first bay has a width of 6.5 millimeters, the second bay of 5.5 meters and 6 meters and so on. The first floor is, the first floor we made it 12 feet high. All the other floors are 10 feet high, which is typical for a commercial building, and so on and so on. So what we're going to do is we're going to see how we're going to be able to model this with ADA. And ADA has, just like it had for the trusses, it has a generator for frames. Okay. So we're going to take advantage of that feature in the program. So now I started a new file. Like I said, every time I start a new file, I'm working in metric. I just want to make sure that file, project configuration. Okay. So preferences, I am now in metric. I want metric sizes when I'm going to be asking for metric designations. And of course, I want to take these dialog boxes away from. Okay, now, of course, then what I like to do, I like to see what's happening, the lengths, the shapes. I really don't care about the materials in this case. And of course, I like to get rid of that global axis, apply. Okay, now, step number 1, okay. I want you guys, okay, so here we go. Calculate the reactions and the displacement of node A. The strong axis of the column is perpendicular to the loads. So what that means is that I want you guys to keep in mind, if I have a rectangular section, okay, a rectangular section, the higher dimension here is always a strong axis. Okay, so in other words, if this happens to be a 400 by 300, well, the 400 is a strong axis. And how do I know this? Well, if I calculate the moment of inertia, 1/12, the base times the height cubed, the one that has a higher height is the one that has a higher moment of inertia. Okay, so in other words, so here I have exterior columns that are 400 by 300, and I have interior columns that are 600 by 300, and then the beams all have 500 by 300. So therefore, the beam should also be placed, the 500 being vertical and the 300 being horizontal. So keep that in mind. Clear the drawing. Okay, so now, on the next page, okay, I'm going to show you, all the steps are here on the next page, okay? And we're going to do this slowly. So we've already set our preferences and all that. So right where we had the truss, right, go over a little to your left, you have building generator. Who does not see this on the second row of their top ribbon? Are we all good?
Yeah.
Can I click on it?
Yeah.
Okay, so here you have a series of tabs, okay? So now, what you're going to have is, for example, this is a series of tabs, okay? coordination. So in other words, it's telling you, do you want me to start at 0, 0, 0? Yeah, always start at 0, 0, 0, unless you're going to put it specifically somewhere in your model that it starts somewhere else. We'll leave it at 0, 0, 0, and the angle is 0. Now, we do not have any two-way floor system in our frame, so therefore put null. If you leave that, it's going to give you a different result because it's going to take that into calculating the values. Now, exterior sheeting, I don't have anything, so I'm going to put null. In other words, all I have is a frame. Now, at the base, if you come back here, my base is not pinned. My base is fixed, okay? So therefore, see, they put pin by default because it's the more conservative value, and therefore you're going to put fixed. So that's the three things you have to adjust on the first tab. In other words, we do not have no horizontal surface, we have no exterior sheeting, and the bases are fixed, okay? And that's what I tell you here. So go null, geometry, null, null, fix, null, null, fix, okay? Leave that the way it is. Now, as far as the numbering system goes, unless you want to change this, but it's telling you how it's going to number each node. I leave that by default. It looks good to me. In other words, the first letter is going to be a lowercase a that represents the X value. The second one represents the Y value. It's a number. And the third one is going to be an uppercase. It's going to represent the Z value, okay, where it's going to be along the Z axis. So I'll leave that the way it is. Just skip it. Now, the X axis, let's go back. So here is what you're doing. You are moving along the x-axis. So what it wants to know is that where is going to be the first row of columns for your frame, where you're going to have your second row, where you're going to have your third row, and so on and so on. So if you have 20 rows, you're going to have, okay, so that's what they're asking you here. So therefore, I'm going to have 1, 2, 3 of them. In other words, I'm going to have 1 row of columns, 2 rows of columns, 3 rows of columns, number 1. And the first row of column is spaced at 6.5 meters. The second row of column is spaced at 5.5 meters. And the third row of column is spaced at 6 meters, okay? Now you notice that the program by default, okay, okay, it had 1, 1, 1, 1 because it has to give itself a value in order for it to continue to do something, and it used 1 meter by default as the distance between the rows, but you simply change that. Now, that's the distances along the x-axis. Now, y-axis is the spacing between each story. So therefore, I'm going to go to the y-axis. And of course, I have 1 story, 2 stories, 3 stories. So I'm going to have 1 story, 2 stories, 3 stories. And it starts with the very first story, which happens to be at 3.6 meters. The second one happens to be at 3 meters. And the third one happens to be at 3 meters. So what the program is going to do now is going to place each story or along the, the grid, the coordinate system properly. Now, since we're not creating a 3D model, we don't have to worry about the Z, okay? And that's why I say skip the Z axis. If you were doing a 3D model, then you would give it the dimensions in the Z direction, and that's what you would do. Now, for materials and sections, okay? Materials and sections. Now, what you're going to do for materials and sections is that, first of all, you're going to tell it whether it's a steel, wood, okay? So you're going to tell it that it's a concrete project, okay? It's not timber, it's not aluminum, okay? Don't worry about the thickness of the plates. We don't have any, so it won't bother. Now, I'm telling you that the concrete strength is 30 MPa. Well, this is concrete. This is the 30 MPa concrete. If it happened to be less, then I would just go in here and I would take, so this is 25 MPa concrete. This is 30 MPa, 35. So it basically has the strength of concrete that we normally use in design, starting from 24 structures, 25, 30, 35, 40, and moving up. Okay, so the material is good by default, both for the beams and the columns. So I don't have to change nothing there. The plates, I don't have any, so I really don't care. Now, as far as the beams go, okay, my beam sizes here are, 500 by 300. Okay, so those are my beam sizes. So therefore, I'm going to go to beams. I'm going to click on this. I have 500. So I'm at the 500 by 300. So I got to make sure I have a radial button there, 500 by 300. If it happened to be a different size, I would definitely go pick a different size. I press OK. So those are my beam sizes. Now, unfortunately, you cannot assign, you can only assign one column size to your frame, and then after that, you're going to go change it. So what I tend to do here is I look at which is a column size that is mostly repeated in my frame. Now, in this case here, it doesn't make much of a difference because I have 3 columns on the exterior and I have 3 columns on the interior. So it makes no difference whether I want to assign the exterior ones or assign the interior ones, but I can only assign one section. I might as well assign them here, so this way I will have to minimize the amount of changes that I need to do afterwards. So what I'm going to do here is I'm going to need to decide to assign all the exterior columns or all the interior columns. Which ones do you guys want to assign, the exterior or the interior ones? Tell me.
The exterior one.
Let's do the exterior ones. Therefore, the exterior ones are 400 by 300. So therefore, let's go to the exterior ones. 400 by 300. Here you go. So I change the radial button from there to that. And of course, not all the columns are going to have the same cross section, but we can go and modify that very easily. Press OK. Now, if I'm happy with all my input, at the very end, okay, at the very end, if I'm happy, I press OK. And the program generated the frame for you. And that's pretty neat, okay? So you see here, you got concrete, 400 by 300, that's what you want, 400 by 300. This is 500 by 300, 500 by 300, and so on. So the only ones that you have to go change, basically, are the interior ones. Okay, so like I said, by default, it assigns the same thing. So what I'm gonna do now is make sure I am on member. I'm gonna activate the member. And of course, I'm gonna go pick these columns, hold the control button, pick these columns, hold the control button. So, and I'm going to change them all at the same time. So now when I'm going to right click on these, go to properties, I'm going to go to properties. Of course, now I'm working in concrete, rectangular, concrete, and here are all the shapes. And we said that the interior ones were 600 by 300. So I'm going to go to the 600 by 300, and there you go. And this way now I press OK. I don't have to change the concrete, so here you go. So now I know that these are 600 by 300. That's what my interior columns are. These are 400 by my exterior column. So as far as the properties go, they are all the right properties. And now, and I've got the right lengths here, 666, 555, 3.6 meters. So everything looks good. It's the right material, concrete, and then of course, I can go to elements, I can take off that and that. I can move this over here and I can say, just make sure I have the right materials, apply. It's all concrete, it's all good. Press OK, now it's all gone. Now, just like we did with a simple frame, we need to make sure that our columns are oriented in the right direction. So what we're going to do is, of course, go to visual objects and we're going to say, show me my things in 3D, just like we did before. So we go to visual options, go to attributes tab, and click on 3D, press apply. And there, that's how it shows it to you in 3D. Now, just like we did with the simple frame, we're going to go to the camera. I want to look at it sideways so I can take, okay, front. Now I can see here that the longer dimension is not perpendicular to my load. So I need to rotate them, okay? Just like I did the other one. The only difference here is that I'm going to pick, first of all, I'm on member. I'm going to pick one member, hold the control button, pick another member, and pick another member. Unfortunately, you can only do one vertical series at a time, okay? Now I'm going to pick rotate. Now, I don't know where I'm rotating about, so I'm going to cancel. I'm going to go back to visual. I'm going to ask for my nodes. So give me my node number so I can see what I'm looking at in terms of my nodes. Apply. So now I have an idea where my nodes are. I have small a, capital A0, small b, capital A0, small c, capital A0, and small d, capital A0. So these are my nodes. Now I go back to rotate. Now I want to rotate by 0 degrees. In other words, just bring them back. And about which node do we want to rotate? Well, put in a small a, lowercase a, capital A, and put in a 0. So the program knows what to use to do its calculation. Press OK. And there you go. Now the columns, the wide part of the column is perpendicular to the load. They're in the right direction. And then again, do it to the next series of columns, vertical columns. Hold the control button. Again, go to rotate. And now this is BA0. So it's small b, shift A, 0. That's the node. I'm sorry. I don't know what happened. Oh yeah, I hit the control button. Small b, shift A, 0. So that's the node I'm rotating about. Press OK. And nothing happened. I guess because I did it wrong. Because I didn't change the angle. Sorry. Small b, shift A, 0. Okay. And there you go. So now I've got the long part of the column in the direction, which is the strong axis, and I keep going. And so this is very important, guys, that you have to make sure, because like I said, the program by default puts it in a certain orientation, okay? Now, I can show you how to change this with the beta angle without having to put the thing, but you might have a problem understanding the beta angle, so I'd rather keep it simple for now. And like I said, rotate, again, 0, and the angle here is C, capital A, 0. Okay, and then last but not least, the last 3, hold the control button. Again, rotate it 90 degrees, it'll go back to 0. And this is D, shift A, 0. That's the node. Okay. And there you go. So now everything's oriented in the right direction. And look, my beams, I don't have to do anything. You have the long long dimension in the vertical position, so that's in the right direction. So everything looks good. So that's so far so good. As far as my model goes, and of course by default all the supports are fixed, and that's what I want, so I don't have to go back and do anything to the supports. Now I'm ready to, I like to go back to what I like to usually see. So like I said, I don't like to see things in 3D. You can leave it the way you want, guys. You're the ones that are working with the program. I take off the 3D, number 1, and I like to go back to the camera and do it right. So I see it in the way that I usually see it. It's up to you. Now I don't need to need my node numbers anymore, so I can go take that off the screen. I go back to elements, take off the numbers for the nodes, apply. Okay. So now I basically okay. So now I basically okay. I basically done my model. I've oriented all my columns in the right direction. Everything is fixed. Everything's good. I'm ready to apply my loads. So I'm ready to go do my loads. So I'm going to go to loads. And I'm going to load cases, define, and of course, leave the dead load. And I'll tell you to leave out the dead loads, and I'll tell you why, because I want you to see this just with the lateral loads to see how it affects the structure. And then if you want, you can do another little combination on your own and run it and see the difference. So I'm going to call this one, like I said, okay, I'm going to call this, like, I can call this a win load. It can be a win load, whatever, and I can go ahead and define it if I wanted to. That's up to you. Okay, and if it's a win load, define it as a win load. It's, you know, I said it won't make a difference here. Now that I define my load, I'm going to activate my load. I'm going to go to wind, save the project, yes. And therefore, let me go to, let me just, okay, so now I save my project, I'm ready to go. Now, like I said, since I'm applying the load at a node, I'm going to activate my node here. It's the simplest way to do it because it's going to be applied right at that node. I click on that node, I double click on that node. Now I'm applying it in the X direction and it's going from left to right. So therefore it's positive 150. Press OK. And there, That's the fastest way to apply the node. And then I go to the next node, double click on it. And of course, it's positive. It's going from left to right. It's positive 130. Okay. And last but not least, the last one, and this is positive 120. Okay, so now my loads have been applied. I don't have any other loads, so therefore I'm ready to do my load combination. So I go to loads, load combination, define my load combination. Of course, I'm going to call this one, I'm going to call it a lateral load. Lateral, just so that when I'm looking at my results, and of course here, all I'm going to do is call up my wind load, which is my lateral load, press OK. So I've done my model, I've applied my load cases, I told the program how to combine my different loads so I can look at the different analysis that I want to look at because the code tells me to look at different things. And now I'm ready to do the analysis, FX, yes, analyze, and guys, you guys don't appreciate, when we had to do this in the old days, it would take us a day to do this. And this was done in a matter of seconds, okay? Close, okay? And of course, you want to see the results of the lateral loads. Now, like I said, what I want to see, like I said, calculate the reaction. So guys, don't do yourself a favor. Activate the reactions here. Okay, activate the reactions and then go do it systematically. I don't care how you do it. If you're going to start here and go there or go from here to here, activate the reactions. Just double click on one. Okay, and look at the reactions. So therefore, you're going to come here. You're going to say, oh, negative 52.73. So right here, you're going to make a little sketch on your paper. You're going to show this going this way. It's negative from right to left, and you're going to be putting 52.73. And that's how you see it. The next one, oh, it's negative. So therefore, it's downward. This is the Y reaction, downwards. And this is 84.95. Oh, it is a positive moment, therefore it's going counterclockwise. So I show it like this, and then I would put the value here of 114.48. Okay, and then once I finish this one, I'm happy with that one, then I would move on to the next one. So in other words, I would go to this reaction and do the same thing. Oh, again, negative. And what I want you to appreciate, okay, negative. Oh, okay. So negative, that means that it's going for the X is going this way. And this is 148.13. Oh, negative again, okay? And going downwards and put the value. Oh, a positive, so therefore counterclockwise. And you press OK. And then after that, you go to the next one. And look at this. What I like about this is that all of a sudden the Y is no longer negative, the Y is positive. So therefore the Y would be going upwards. The X is still negative, so it still goes from right to left, but the Y has changed direction. As far as the moment goes, no, it hasn't changed direction. It's still counterclockwise, okay? And that's why, guys, it's better you do it this way than try to read it off the screen, because year after year, people try to read it off the screen, because here, I'll show you what happens. Okay, year after year, people read it off the screen, and this is what happens. They come here, they do this, they say results, Rx, Ry, okay, and then MZ, okay, that's what they do, apply. Yeah, they see the X, they see the Y value, but you don't see the MZ value. So they just write this on a test paper, they forget the MZ, they get 0. Okay, so do yourself a favor. Here there is an MZ value, okay? In other words, there is a rotation about the Z-axis. So do yourself a favor. If you want to make sure, you can do it both ways, but if you want to get an idea of the direction, but you notice here, it points downward, but it doesn't give me a negative minus 80.95. It just gives me the right direction and the right value, the right direction, the right value. And that's what I want to see, the right direction and the right value. And like I said, when it comes to the moments, the way the program tells you which one is clockwise and counterclockwise, it takes counterclockwise to be positive, okay? And now, if I ask you for the displacement at point A, the displacement at point A, so I'm going to go back to here, I'm going to activate my nodes. I'm simply going to double click on that node here, and it's going to tell me exactly what the displacements are. So therefore, the displacement here at node A is, okay, the displacement is like in this direction is 18.16 millimeters because it's positive, and in this direction here is downwards because it's negative 0.17 millimeters, and that's what I'm going to expect you to see. Should give me as the results of your analysis. And if you modeled, like in other words, if you didn't change the orientation in the right direction, or if you put the wrong cross section, this is where I'm going to be able to tell right away whether you did it right or wrong. And if this is wrong, I will give you, because that means that something's wrong with your structure. And I will not ask you for your files, guys. I will only base myself on what you hand in your test papers. And I don't want to see no screenshots. I want to see everything sketched and then put on the sketches. If you give me a screenshot, I will give you 0. No screenshots. So get into the habit of doing your sketches and transferring the information onto your sketches. Okay, and basically that's it, I think, for frames. So I hope you guys have a better appreciation of what this program can do for you in terms of analysis. Like I said, in the old days when we used to do this, I would spend one day to do the analysis of this one frame. And now I can do this within a matter of 10, 15 minutes. And the nice thing about it is that once it's modeled, if all of a sudden I want to do different load cases, I can do different load cases. Whereas before, if I want to do different load cases, I'd have to spend different days to get the results. And so this program is very powerful. And like I said, it's it can also do it in 3D if you want, but we won't go there. Does anybody have any questions? I think that's it for. Oh yeah, so here are the okay. I should have changed the orientation, but that's it. So that's it, guys. Does anybody have any questions before we call it a day? Are we all good?
Yeah, I'm good.
Good. I'm glad to hear, guys. Like when I ask you a question, please come in and say something, because I feel as if I'm talking to a screen, you understand? Okay, so I'm going to stop sharing. I'm going to pause the